morning to everyone. I'm Gonzalo Avellán. It's a pleasure to me to be here in Valencia again, and even more to present and welcome Fabrice Leroux. He's coming from Clermont-Ferrand. He's one of the world leaders in LDHs. He's the typical author that when I was doing my PhD, I was always citing in the beginning. So he wrote one of the best books in LDH I ever read in my life. So I mean, for us, it's a pleasure. For Jose Alberto, tomorrow in the PhD defense will be even better, I think. And he's now becoming the director of the Institut de Chimie in Clermont-Ferrand, which is a very important position, I would say. And he's also an expert in the applications of LDHs, which is not the most treated topic in the papers of LDH that we used to read here. And he has a strong collaboration with a chemical company, BSF, which is something that I would say is worth to pay attention in the talk. And please join me welcoming Fabrice.
Thank you, Gonzalo, for this very nice introduction. I will try my best to honor these nice words that you mentioned, and the importance of application. So first of all, I would like to thank you, Sir Eugenio Coronado, for your very kind invitation to be here in Valencia. I really appreciate it. It's my first time here. So it's a very nice to be with you. And thank you, Gonzalo Avellán, for to be member of the Defense Committee of Jose Carrasco. So it will be a pleasure to meet again tomorrow. So it's a long title. So as you mentioned, I will deal with academic and application for LDH. So layered double hydroxide nanoplatelets, Ubiquity, Topochemistry, and Corrosion inhibition for polymer coating. So I will show you briefly, and I will try not to be too long, that LDH can cover quite a lot. There will be probably no magnetism, because we are the center of excellence for magnetism in LDH, but you will see some electrochemistry, some polymer filler aspects, and so on. And as we mentioned, it's been done in collaboration with a German group, BSF, and during 10 years, and filling a lot of patents and so on. So it was quite a nice collaboration. So first of all, let me introduce you the Chemical Institute of Clermont-Ferrand. So we are here in the middle of France. That's the area of the old volcanoes, the ancient volcanoes. You may have already seen some Volvic bottle of spring water. It's coming from there. It's, I would say, connected, not very well sometimes, to major cities like Leroux, like Paris, by train mostly, or airplane. And you have here Montpellier. We are in the Institute 6 different research teams covering different aspects, inorganic chemistry, organic chemistry, and physical chemistry as well. So in terms of photochemistry, inorganic materials, that I will cover that later on. Healthcare materials, so for like bone repair, for instance, organic medicinal and chemistry, and some biocatalysis and metabolism, and as well as thermodynamics and molecular interaction. This group has a quite close relationship with the company. So it's working with Orano, the new name for Areva. So we are working with uranium combustible. So that's a hot part of the lab. And this team is working with Michelin to anticipate what's going on in tire. So for modeling elastomer versus silica filler interaction, and how we can improve and to get better design for that. So focus on the inorganic material part. So we are working on the different designing, elaboration, characterization, and to process, and as well as to think on what will be the next step to recycle and to use the byproduct, or to the gravel to grave cycle for materials. So that's more and more of topical need, because we need to think on that. It's a demand from our society. So we cannot just produce and put on the market things that we cannot get rid of easily. So the focus is on the luminescent material, like lead, labeling techniques. So as I told you, that's the Orano working with fluorinated materials, UF6, and plasma process material, as well as lamellar materials. So I will focus on the last one because it's my area. That's the layer double hydroxide team. You may have met some of them. So Claude Forano, Christine Mousti, Vanessa Prévost, Guillaume Renaudin, and Christine Taviogueo. So they are all complementary in terms of expertise. Claude is more environmental, Vanessa is more on the synthesis, Christine Mousti is more on the electrochemical part, bio, sensor. Guillaume is more on the cement application, and Christine is more on the X-ray analysis and structural characterization. So we focus on, of course, LDH, and I will show you briefly the structure, but you may have already see that. So elaboration and structure properties to finally get into different application as photodegradation, electrocatalysis, biosensor, biocatalysis, and bioremediation, coatings for anti-corrosion, biocide, and many other properties, energy storage, and as well as cement. Cement, you may say that's quite particular, but in the form hydration of cement, one part is a calcium aluminium, it's an hydrocalamite, and is kind of a member of the big family of LDH. That's the reason we are working on that, and that's the only component that can expand in cement system. So it's kind of interest putting, for instance, plasticizer. So to work on the workability of cement now and anti-moisture and so on. So that's a lot of chemistry involved. Even if cement is very well known from ages, so you still have some things to do on that. So I will focus mostly on this part because that's my area, and a little bit of this one. So as you know, LDH has a layer structure, edge-sharing octaedra, planar, and it's a substitution of trivalent, of divalent by trivalent to form from the prussite magnesium dihydroxide to form some kind of complex structure like that. Positively charged in the layer, and so you have to compensate with the presence of an ion in between the layer. And thus give you all the versatility and the tunability of the LDH structure, because you can tune, you can change at will the nature of your anion in between the layer. So it can be DNA, for instance, for gene reservoir, or can be superplasticizer for cement, can be anti-UV, biocide, or anything you want, or something magnet that you want to put in between the layer. And you can change the nature of the cation, nature zinc, magnesium, cobalt, nickel as a divalent, and for the trivalent, aluminium, iron mostly, but chromium as well, and many others. So you have a large tuning in terms of intra-layer composition, as well as the ratio in between these divalent and trivalent. So they're directly related to the loading of anion in between. So if you substitute more divalent by trivalent, you have to put more anion. So you can load even more anion. So that can be of interest if you want to do, for instance, in situ chemistry in between the layer, and that you want to connect molecules, or you want to isolate them. So it's like a game. You can play with that. So in the team we are concerned about LDH elaboration, because we try our best to design LDH materials by anion exchange, calcination, reconstruction, electrogeneration, organic sol gel, co-precipitation. I know that you are aware of many of this way to produce LDH, for instance, the hydroxide way, and hydrothermal as well. So it's just to see what will be the shape and to control the last shape you want for LDH. For instance, large particles, so you may favor supercritical drying or some spray. You want maybe to design as a foam because of the porosity to get a large interface with the outside medium, or you want microsphere because you want to disperse that into polymer, and so on and so on. So that's at will. You can adapt what you have here to produce the shape of LDH particles. Shape of LDH particles, as well as the rate of aggregation and conglomeration, because that's a trick part. That's to avoid sometimes that these nicely shaped or stacked platelets, they can glue together, and after it's very difficult to disassemble the secondary stacked assembly. That's a trick, and that we will see in terms of application. It's a key factor. In terms of characterization, it's very important of course, to characterize at best our LDH sample, and for that we use time-resolved in-situ energy dispersive X-ray diffraction, so that you use synchrotron, and it's really, in this case, spectrum, X-ray spectrum, because it's energy dependent. It's not it's a complete white beam that you are putting on your materials. It's just not copper, so you can tell a spectrum. Otherwise, it would be diagram, of course. And you have the exchange and the staging phenomenon that we observe at on this sample copper chromium. We can do a 2D mapping, so 2D density in between the layer for this kind of molecule to check if they have some gap in between, or if that's completely corrugated or conjugated in between the layers. So that's interesting to check the electronic density map as a function of the relative harmonic intensity here that you can get after a Fourier transform of this X-ray diagram. And you can get as well, using Rietveld refinement, you can get the anisotropy as well as the shape and the coherent length according to the X-ray analysis. And we use also different methods like synchrotron in Paris, in Soleil, to do the pair function distribution. I will show you briefly after. So that we have done X-ray on this one. Yes, that's a cobalt aluminum or cobalt. We can get the pair function distribution from the X-ray recording, and at a very high Q under a synchrotron, and you can get, in fact, all the couple, the pairing atom inside the structure. So it's a very local probe using X-ray diffraction. So it's very neat. In fact, what you do a Fourier transform of all that. You go down to more than 120 into the inverse space, and you can get such information. So that's very important. And when you are looking at, for instance, neighboring, like a magnetism center inside the intra-layer information, you may have some information and some very clear information on the local order. So that's been done on these topics. I will cover very briefly what we have done in the past in terms of LDH and energy, because it's not obvious to use LDH platelets or composition for energy. At first, we use layered double hydroxide for the confinement of organic species that can produce carbon during carbonization, because you use the confinement of the layered structure to yield carbon. Why it is of interest? Because in fact you confine the carbon species and you get a porosity, macroporous carbon. So when you do so, you have some styrene benzene sulfonic acid with zinc aluminum, for instance. That's this supple, that's a flex like texture. You burn under nitrogen or inert gas, because you don't want to get rid of all the carbon species under CO2, and you get some kind of a stone here. There is no porosity at first, and after when you calcine at in temperature here under nitrogen, you get a macroporous here, macroporous porosity. You can see here by the steep rise of the absorption at a low relative pressure, but you have nothing else after. You have no other porosity, and you acid leach what is here, but the small inorganic particles coming from the breakdown of the LDH, and you get rid of that, and it's acting as a corrosion, as a pore agent, forming agent. And when you do so, you end up with a very large surface area, keeping the microporous here surface as well as the mesoporous activity here, because you get rid of all the inorganic part. So you get a dual macro meso carbon, mesoporous carbon, so it can be of interest for all the supercapacitor applications in terms of energy. So it's a system based on the capacitive behavior of electrochemical storage. It's not a lithium-ion battery, so it's not a Faradic behavior, but it's on the surface, so it's acting very rapidly, so it's a very powerful system. Not too much energy, but a large power efficiency. So it means it's very interesting for all the ignition or the feedback in a very short period of time. If you need a large power in 1, 2, 10 seconds, you will need a supercapacitor. But for a long-term energy demanding, it will be a more lithium-ion battery or some other electrochemical storage, but with a large energy. So that's today is very interesting. If you look at the literature, they try to combine, in fact, very high power supercapacitor with storage lithium-ion battery to get a dual system, very powerful and very good in energy, in time. So that's a dual system. So in fact, that's what we try to do in one step. Instead of using only the confinement using passive LDH structure, we use iron, cobalt, host structure with a carbonization. So we end up with some carbon and small particles that you don't want to get rid of it because they are maybe potentially electrochemically active. So you may have some Faradic process if you go slowly enough in cyclic voltammetry. You can see that here it's 0.1 millivolt per second. So you can see the Faradic process because it's a low electrochemical process. You have to oxidize and reduce. So it's a redox activity. It's not only a surface activity. And when you go to very high speed of cycling, like 200 millivolts per second, so it's a very powerful, very rapid, you get rid of the Faradic, but you keep the capacitive behavior. So you have a dual system, very demanding in terms of power, but you keep some energy as well. So that's been done on this kind of system. So on the talk here, I will focus more on the filler aspect for LDH. So the reason why LDH platelets are of interest for polymer filler, so I will show you briefly why, and how we use LDH to develop solution for coatings for more than 10 years with BASF. And yeah, some curiosity or ubiquity of LDH. It was not very nice for the company because it resulted in a good, nice article, but the solution was not very interesting for the company. I will say. I will tell you why, and some property in terms of corrosion. So, as you may know, nano composite has a lot of attention right now because compared to macro composite, in which the filler dimension is very large, or the micrometer, so the interaction is rough. You have almost no interaction, and you can anticipate, in fact, the properties in that assembly of filler and, for instance, the silica glass mixed with a polymer, whatever. You can anticipate, or you can calculate the mechanical Young modulus, for instance, just by a mass law between the two, because the interaction is about 0. You have no interaction. So you take the Young modulus of one part and the other part, you add and you divide by the sum of the two, and you almost get what you will get at the end. So it's a high modulus glass fiber, and here small modulus, Young modulus of polymer. When you go down to nanometer scale for the filler, the interface is preponderant. It means that the interaction between the filler and the polymer chain are dramatically enhanced. So you cannot foresee, you cannot calculate anymore what you will have at the end, because the interaction is in fact the best part. That's the gluing together between polymer chain, between the gyration radius of your polymer chain, in contacting, in fact, directly the surface of your composite. And the filler can be, of course, of different dimension, can be 1D, like a carbon nanotube, can be layered structure, and you can delaminate or exfoliate such a bidimensional framework, like LDH, or you can use 3D, like quantum dots or POS, polyoxoxane. Why of interest using LDH? Because you have the anisotropic platelets. So you know that you have a form factor very large. So it means that the lateral size is quite large, and the dimension between stacked layers are short. And if you go and you reach the single platelets, your form factor is quite big. It can be as big as 1,000. It's no dimension, because you divide the lateral side by thickness, and you get a number only. On top of that, you have some tortuous paths, because you have some anisotropic objects. So it means that if you want to cover some packaging, for instance, application for polymer, you want to avoid gas permeation, like oxygen or like water, to go into what you try to protect from the outside. You have all this barrier effect, so that's of interest. And knowing that you can tune the composition, the intra-composition, you can tune also what is inside, so you can release what is inside the LDH, so you can have an active or self-healing component. And this was the idea behind that, to use LDH as a filler for polymer coating at first. So we try to, we have been working on that for inhibition corrosion, and I will show you that later. Yes, so that's a scenario, and I will comment that later on. Just for you to better understand why we were interested in that, so it's for painting, but not only painting for outside, it's for plane, aircraft, for car. So you have to be robust, you have to get into the last technological polymer. So I draw some improvement along the different period of time. And as you can see, we are more and more concerned of what we are putting as chemicals. That's true everywhere. So it means that few years ago, many years ago, we didn't care about volatile organic content, because we were working with organic solvent all the time. Now it's almost forbidden for large diffusion of materials. So it's a waterborne paint from 90s. We have now to avoid all what is CMR, so that's a cancer, reprotoxic and mutagen products, so that's completely to avoid. And even some other that are blacklisted at the European legislation, so you cannot work with what you want. Chromate is forbidden now in a large diffusion. And it has to be sustainable. It has to be green as possible. And you have to recycle it. All that together, and still you have to be, in terms of price, very, very of interest. Because it's a company. They are philanthropic, but not that much, of course. So what we decided to, because we work different solution, and we were quite pleased to try to generate Institut platelets directly inside the polymer coatings. So that would be a zero chemical impact and directly forming the LDH into the polymer. But of course, no excess of initial chemicals, so everything put inside has to react. And you have to find a good process, as we are talking just earlier. The process is very important to produce LDH materials. So we focus on the hydrolysis of metal acetate in a alcoholic polyol medium and ammonia. So that's, and in fact, it's efficient to produce layer single hydroxide and layer double hydroxide. You will see that. So, ubiquity of LDH. So when you put both acetate salt into your waterborne polymer, one component of what you will get at the end on your car, you get the purple X-ray diagram. And I don't know if you're expert, but trust me, you have not here reached the LDH, but you have reached the LSH, because the two theta here, I will show you next slide, are completely characteristic of LSH. So it means that something wrong happened. There is only one metal, acetate, reacting to produce a layer structure, which is quite different, familiar, closely related to LDH, but not too much. And in time, because we keep the polymer coating to in an inert atmosphere, and in time we get LDH. We have a shift here. I'm fine, it's quite of small value, but it's significant to address if it's LSH or LDH. I will show you. If we do the experiment with no polymer, shows that's reported in the literature. So you have the zinc aluminium LDH here, and the peak here is a 110 directly related to the cell parameter. So it's a mixture of cationic radius zinc aluminum. So it's here, and it's as this yes. And you have here no, is that the opposite? Zinc aluminium is here, and yeah, no, that's this way. And you have the zinc LSH layer single hydroxide here. So that's small, but that's significant. So for the LSH, we have prepared LSH directly into the waterborne polymer, and you can see that we can get the LSH single metal acetate and forming the LSH inside the polymer, and you can see that we have formed the 2D structure. There is no problem. And in temperature and under TEM, we can see the layers of LSH, and it's even expandable. That's quite unusual, because it has been reported in the literature that layer single hydroxide is very prone to keep its basal spacing intact. It's very difficult to move, to prop apart the LSH layer structure. So that's quite interesting to do. So the reason behind is very surprising, because if you compare the LSH to LDH structure, LSH is the, in fact, edge octahedral sharing structure, but you have some vacancy, octahedral vacancy, and on top of, below of this vacancy, you have the tetrahedra, and center of the polyhedra, octahedra or tetrahedra, you have the same cation, the same metal, like zinc here. In comparison to LDH, you have That's the opposite again. No, it's not. Okay. It's zinc, aluminium is here, and you have aluminium and zinc inside octahedral, only octahedral, and you have no vacancy. Yeah, you have to change. You okay? Here it's only zinc is here and zinc aluminium is here. So that's the main difference. That's the vacancy, no vacancy, tetrahedra, octahedra, and so on. And you will see that on different transition methods it makes sense because you may have a change of color because you change coordination, and that's a fingerprint that we are been using to address the difference. I will go very quickly on that long slide because just to show you that we didn't invent everything. It was present in the literature quite a long time ago that LDH can be formed on the surface of magnesium hydroxide, can form on the surface of aluminum because it's a ubiquity of LDH. If you have the a good pH, and it's quite large of value, you can yield LDH at the end of a reaction just on the surface of a metal if you add some aluminum hydroxide, for instance, or some nickel or cobalt. And at the end, the final product that you will get, passivating the metal surface, will be LDH. And the same for lithium aluminium. If you want to trap lithium, it can be from in the case of different waste company using lithium, you can put aluminum at a certain pH and you trap to form lithium aluminium LDH. And more recently, it has been performed by the group of Professor Sasaki in Japan, and they were doing some cobalt nickel tunable composition directly from cobalt or from nickel hydroxide. And so, as well as a conversion of cobalt from beta cobalt dihydroxide. So it looks like everything is possible. Of course not, but a large possibility is available in terms of LDH chemistry. And so, return to our affair here. Why and how will be the mechanism involve transforming LSH to LDH? So first of all, just to prove you, to show you that's really the case, so we record in time all this X-ray diagram. So from the starting point, so 0 to 85 days, and of course it's dependent on the temperature. The more you eat, less time you need to transform LSH to LDH. But you have a change here, a shift of this diffraction peaks, which is completely characteristic of your cell parameter. So the presence of two cations or one cation. And as well as here, it's a 1, 2, 0. So it's the alkaline diffraction line linking layers and the interlayer. And of course, if you look at the LSH is more ordered, and you have less ordered structure for LDH. Everything is okay in that sense. If you look at the transformation under TEM or SEM, you can see that in fact the limiting factor is aluminum acetate. Even if you are using the polyol in temperature, temperature is not enough to grind or to dissolve completely the aluminum source. So you end up with some aluminum still present, and the zinc is already reacting to form LSH, zinc. And little by little, the aluminum gets porous. You have some grinding of this aluminum form, even if the temperature is now cooled down because the reaction is not anymore available. It's trapped into the polymer medium. And little by little, the aluminum is transforming, and it can fragment to get some airy here domain, at which, in fact, the LSH are reacting with aluminum dissolving and forming LDH little by little at this time. And you can see that from the form layer structure at 0, at the starting point, you have already a layer structure, so that's LSH. and very small lateral size. And little by little, you have the lateral size dimension is growing up. And you can see here all this. And at the end, you have the LDH. In terms, and that's more interesting here, it's at the interface where you can see that there is no interface here, and you start to see some evolution at the interface here. And little by little, you start to form the platelets just in the vicinity of the ground, of the grain, of little aluminum-rich domain. So that's the observation, and we were quite keen to know what would be, in fact, for this topochemical reaction, quite unusual to unravel, what were the kinetics information, because we wanted to know what kind of mechanism is behind that. So to do that, and that's the reason it's quite small value, but still we can refine, so that the position of the LSH and the position of LDH all together to be at the intermediate time at which you have both together, LSH and LDH. And you can, of course, refine the presence of one or the other in some kind of solid state kinetics analysis. It's 1 minus alpha and alpha, so you have a transformation step of one phase converting to another one, LSH to LDH, and versus temperature. So you get all this conversion rate, and that's a rate of conversion for LDH. And if you do that in temperature, you have access to the kinetics parameters and, of course, to the activation energy. And if you draw this K versus inverse of temperature as an Arrhenius type of graph, you end up with an activation energy of quite consistent, more than 100 kilojoule per mole. If you compare that to different layer structure, because of course you have to compare with the same dimension and the same kind of type of materials. Lithium into gibbsite, for instance, into aluminum trihydroxide, so just lithium diffusion into the vacancy, 1/3 of the vacancy of the gibbsite, give you activation energy of 27 kilojoule per mole. So it's quite far from that. So probably it tells you that's probably not diffusion. If you check, in this case, the from a layer prephase to form aluminum silicate phosphate, SAPO, and that's been done by the group of Professor Ware in a few years ago, you get 160, and they justify that by a dissolution and reprecipitation. And when you think on that, of course, it can be only dissolution and reprecipitation, because if you have aluminum reacting with LSH directly, the inside layers will be completely not untouched, because you will have a blocking reaction by encapsulating LDH surrounding LSH, but you will have no migration, ingress of aluminum inside your LSH anymore. So you have to dissolve and to reprecipitate again, because otherwise it will be forming LDH repulsive to aluminum ingress. And it has been as well mentioned in this kind of formation, inclusive hydroxide in other phase, hydroxycarbonate. I will stop here for that. A nice thing that we can generalize that. So working with zinc in PVP, polyvinyl pyrrolidone, so we change the medium. We end up with zinc dihydroxide, T0, versus time zinc aluminum again, because of the aluminum poor reactivity, but still involving in time and at 40 degrees C. We have been working with different other composition, cobalt, using cobalt aluminum, and at first when you do the reaction into PVP and using the same reactant at the same temperature, you end up with LSH, and in time you end up with cobalt aluminum. And that you can tell because the color is completely different. You have the blue color LSH because you have octahedra, tetrahedra, cobalt. That's completely consistent with the color chain between LSH and LDH. And at the end, you have the ingress of aluminium 3+ into the LSH by dissolution by precipitation, and you form the LDH. And we have complete that with the copper. And in the case of copper, it's even more appealing because, in fact, the LSH is a very we will say that is strongly distorted, but you have no vacancy for this copper structure. So it means that the reaction of aluminum into this copper LSH can only be by dissolution, because there is no way, there is no empty voids to diffuse into. Okay, so that was a complete thing. Of course, it's a very nice mechanism. It's nice chemistry, but in terms of application for a company, it's a disaster because it means that you are keeping a powder into a polymer coating, and that is changing in time, and you change form ratio. You have some reaction still going on, so you cannot sell this product to any people. Okay. That's, so it was interesting for us, but not really for them. But it's a way. I don't know what time. It's okay. So the final part will be on the corrosion inhibition. I will go briefly. So here, make everything appear all the time. So it's aluminum alloy. That's of course of interest because it's the metal alloy used for airplane, and it's 2024. So its weak point. It has some copper composition into the alloy, and the idea, of course, to protect this alloy from corrosion is to put in the primer. We call that the primer coat. So it's you have the substrate, metal substrate. You have corrosion protection. Apart from that, by electrochemistry, and after you have different polymer coatings. So the primer and the top coat. So the primer, the challenge is to change the inhibition corrosion that you previously had in this industry, and they were using chromate, and now it's forbidden last 10, 15 years. So you have to find other solution, and usually it's triazole, basotriazole, for instance, and cerium oxide, but it's very pricey. So you have to find things to get it to non-stable. And one appealing aspect is to protect this active additive acting against the corrosion, and to trap them, or to put a vessel or container in which they are protecting from the polymer chain. Because of course, when you are using some organic active species, they are very active, but not in a good way. They can be active against the polymer chain. They can migrate out of the polymer coating because they are of small molecular weight, so they can diffuse. By diffusing, of course, they can break down the integrity of the polymer coating. So when you will have moisture, you will have a path of diffusion for water. So the good thing is to trap the active corrosion inhibition species. And to do so, you may use zeolite, that's been done, halloysite, and of course LDH, because of, as I mentioned previously, the good thing about all the chemistry involved in LDH and the tunability that you have for this type of materials. So we have tried, because we were interested, as I mentioned, on green aspect. So if you want to replace a nasty CMR agent, it's better to go a step further, so to select a green material. So we end up selecting amino acid, and all this amino acid has been tested alone, themselves. Here the yellow circle is chromate, and you can see that from the position of the substrate itself without any additive, it's a little bit higher, so it's anodic protection. And what we have tested that here, that's the L-cysteine, for instance, it's a cathodic protection, and that's the phenylalanine. So those two were selected to be trapped into LDH, because we don't want them to react with no corrosion occurring. And if they are released, it means that there is corrosion, because in fact the coating has been disrupted. So it's a safe healing at demand. They are dormant, they are sleeping. If the substrate is not, don't need the spaces to be released, and when you have some break through the coatings, the organic is released. That's nice. So that's a scenario, and of course you have to check all together. I will go quickly. You have the anodic dissolution occurring from the corrosion, because you have a low pH and you have a dissolution of the metal, and that's a cathodic corrosion in which you have oxygen involvement and you have a lot of chloride. So when you think about the LDH chemistry, very low pH, so it means that the layer structure will be completely dissolved, break down. So you will release naturally what you have been incorporated into at first, so the corrosion inhibition agent. And for the cathodic protection, it will be released by anion exchange because of the chlorine. We have a lot of chlorine into the medium, acting as an aggressive anion, and of course doing some filiform corrosion beneath the polymer coating. That's a polymer coating. So in both scenarios, you may have some occurrence of the LDH to protect or to fight against the corrosion, because of dissolution here and because of the anion exchange here. So we tested, I will not go into too much details, different electrochemical characterization using impedance spectroscopy that can model what is occurring beneath the coating, because you have one electrode is substrate directly, and on the other part is inside the medium, so it's inside the salty water solution that you put in the face of your coating, and you can model in fact all the interface involved. So it means all this interface. So that's the interface here, that's the interface here. So all the interface you can model by a circuit here, and so you can end up with corrosion resistance of your coating. I will not go into too much details unless you have questions here. So we perform that on the uneven substrate for which we track. So we want to release the corrosion inhibitor and to see how it's reacting. So we have a tube here, glue on top of that, and with the water and electrode inside on that. And we wanted also to check the integrity of the polymer, if the LDH system is not disrupting the coating itself. So that's two different systems that we were using. So first of all, to get a big picture of that, if you put nitrate, and it has been identified as a corrosion inhibition in the past from a Japanese company, if you put sodium nitrate directly into the solution on contacting the aluminum surface, it's not good. And it's reacting, it's not preventing from corrosion at all. But if you put a nitrate in between LDH and release slowly and acting as a corrosion inhibition, is much better, and you avoid the blister. So you have some barrier properties when you use the LDH itself, and you can see that there is a decrease here of intensity. That's a Tafel curve. That's the way you measure, in fact, the efficiency of your corrosion inhibition. You can work with that Tafel curve. So that's intensity versus potential, and that's the impedance, total impedance as a function of the frequency. And we eat quite a nice choice, because if you compare, so chromate here in red, so it's quite nice corrosion inhibition. But if you look at the BTS, or benzotriazole, that's been identified in the literature as the most appealing or compelling additives to replace chromate. In fact, we have even a better solution using L-cysteine. So it's an amino acid with a thiol group from the amino group, and interleaved into LDH, and is acting as a very good inhibitor. Alors, it's acting as an inhibitor in that sense that it's not anodic, because it doesn't avoid dissolution of the metal, because here it's black. Yeah, it appears not very shiny in comparison to chromate, because chromate is avoid dissolution. So the surface of the scratch aluminum surface still shiny, because you have no corrosion appearing under the scratch. But here the prevention of protection is even better, but is cathodic protection. So the corrosion is stopped not at the Q dissolution when I show you here. It's not stopped here as a corrosion, but it's stopped here. And when you stop both reactions, they have to be linked together. And if you stop one of them, the corrosion is stopped. So you can stop here, or you can stop here. And of course, we perform some microscope analysis before, after scratch, but before and after immersion in salty water. So you can see on the scratch zinc and sulfur coming from the cysteine, amino acid cysteine, and zinc coming from the LDH. Aluminum, of course, not, because it's aluminum substrate, so aluminum is definitely not the best element to probe. Copper, so it's aluminum copper alloy, and so you have some titanium present because it's in the polymer coating. So that's before immersion, so that you have the LDH and zinc amino organo inorganic LDH at the scratch level, just at the frontier. And after immersion, you can see that if you look at the sulfur and zinc, they are more spread onto the surface here. It's a pink or red points, dots, and protecting the copper and aluminum. So it means that you are really a migration of the zinc and the L-cysteine on the bare aluminum substrate. So we are going now lately for green filler for anti-UV or UV scavenger, and biocide and chain extension for biopolymer. I will not show you that, maybe in a few years when we have a good idea of what will be this technology for our everyday life, because it's of course for packaging application. And we have done some feature articles, all the book, all together, and that's quite nice, because in a few years some of them will be retired. So it was a nice opportunity for us to give one shot picture of what we have performed on this LDH. And so that's some of this part that I show you today. So, and I would like to thank all my co-workers, of course, and would like to thank the BASF company, who pay a lot for this contribution, this inhibition, corrosion, and what is behind. And I would like to thank you for your attention.
Now time for questions, please.
have your system in which you change from SPH, single
layer single hydroxide
to
LDH.
LDH. Well, this situation is completely general or not? I mean, because you have shown with one example that involved aluminium and zinc, but if you change the metal, it's also possible to have
we change the diamond metal. So zinc aluminium, we observe that. Changing the polymer, we observe. So shifting from a polyester to a polyvinyl pyrrolidone, it was the same. Because it's in fact the core reaction of the aluminium acetate, hydroxide acetate. We didn't change the trivalent. We didn't try with the iron. It would be of interest to see if that's something going on. But for cobalt aluminium and for copper aluminium, it's working as well. We have a small transformation in time, even at room temperature. It will take 2 or 3 months. And if you store the polymer in a beaker or a closed beaker and at 60 degrees, it will, in a few days you will convert.
And then you have after you have also said that it's possible to pass from the oxide to the hydroxide.
Yes.
Then it's possible to take the LDH, for example, for generating oxides, or that means it's also possible to do the reverse possibility. Well, I don't know with heating, it's possible. I don't know if it is possible to use this kind of LDH as a source of aluminium oxide, for example.
Yes. In temperature, you can convert to aluminum oxide. But usually at room temperature on soft chemistry route, the final product is LDH.
Yeah, no, the way I'm thinking, for example, if you want to prepare a kind of coating with some aluminum oxide for some kind of electronic application, you need a very thin layer. Then in that case, using the LDH, that is possible to delaminate, and you have already thin layers that can be on the surface. If after you can make a treatment in which produce aluminum oxide, is a way to generate aluminum oxide different from oxidizing aluminum, that is the usual way. Then I don't know.
It has been done to use selective acid leaching, for instance. If you think of using magnesium aluminum, total site of zinc aluminum, you calcine in temperature, you end up with gainite, zinc aluminum, so zinc aluminum 204. That can be acid leached preferentially at low concentration of acid, and you can get rid of zinc, and you end up with aluminum oxide only, very close, that you can convert thermally to a thin barrier. Maybe maybe should work. You have to dissolve. You have to dissolve to get rid of one part.
People working in LDH, they used to think in the way in which, okay, we put that in solution and we see what happens. Then it's always from some kind of initial product, you pass always to solution and you have always working solution. To do the reverse way, to go from the solution to the dry state is can be also a way to obtain.
But this is connected to now there is a debate about the memory effect of LDHs. So in the past, it was thought that was you calcine an LDH, then you put it in liquid with some cations, and then there is a reconstruction of the LDH phase by topochemistry or topochemical approach. But now some people is claiming that this is not true. It's just a ready solution and reprecipitation of the material. So it's quite difficult to force the other way around. So I mean,
yeah, me personally, I don't really like reconstruction work because it's not really the case. Even if that's a pre-spinel that you form, it's amorphous pre-spinel, you are in between end of LDH, not forming stable metal oxide. But in fact, what you have the layer is completely collapsed, and you have almost, but not exactly, the rock salt structure of spinel. If you look at what you have locally, it's very close related, but it's not really. You need extra 1 100, 200 degrees C temperature, just to as a thermal barrier to make it clearly more coherent in terms of order. But and at this certain temperature, yes, it's very close. It's very unstable, metastable. So if you put that in water, it's go back to the stabilized structure, and that's LPH. But it's yeah, you can see that as a front dissolution or precipitation, not really a memoir effect. So,
yeah, that's what I was reading. Other questions?
In case of your LDA structure, so I think water is playing the major role, right, to keep the intact structure. So
yes.
Yes, of course. So if you just heat up around 100 degrees, I think then the structure is fragile, it will break down, right?
No, you can keep the layer structure even if the iteration rate is very low. You can graft in some special case of organic interleaved spaces. You can graft the functional group of your anion on the hydroxide bearing platelets. Because if you collapse or you decrease the basal spacing, your electrostatic interaction between your functional group of your anion and the positively charged LDH can connect together. For sulfate, for instance, it's quite known. You can form some grafting, and of course it's irreversible in this case. And you can go back to room temperature, and you have a stack system. But water plays a major role, but I would say that cation composition mostly, because some composition are stable up to 400 degrees C from some local sites, and other like nickel aluminium or even zinc aluminium is stable up to 250, 300, or even less, not even 300 degrees. Depends on the structure of the mixed oxide or the oxide are formed. Zinc oxide, for instance, zincite is formed at 220, 230 degrees C. And periclase, magnesium oxide, is formed at 450, 460. So it depends on the chemistry involved with the cation oxide itself.
And for characterization, so I think you have mainly PXRD. So why don't you use XPS to know that on the elemental composition ratio and then their oxidation state and how long they are stable and can be?
Yeah, it's a good question. We use usually pair function distribution. We have been using X-ray absorption spectroscopy as well for the local order. XPS, for what I've shown you, we use mostly zinc or magnesium aluminium because of the price and because of the color aspect, because we use that in polymer coating. So they use some pigment, color pigment, in addition as a top coat for the furniture, for varnishing properties, but we avoid transition metal with color. And zinc and magnesium, XPS would be not very big interest. I agree with you with cobalt, iron, that's kind of good interest. We have done XPS on what I briefly show you on cobalt to distinguish between the surface and the bulk with the cobalt system as a supercapacitor to see how quick the system was on the capacity Faraday response, and it was only the surface or the inside bulk response for the wall. So that can be of interest to check the different oxidation state surface versus inside.
And one last question. So did you check that open circuit potential in your LTH, because we have lots of like cation, so I guess the open circuit potential will be like more than 0. Or
The open circuit
potential, yes.
potential.
OCP.
Yes, when we perform some supercapacitor cells, yes, we measure it. I know that have in mind usually. The open circuit voltage, for instance, is what you have for when you measure the Tafel curve. You go for oxidation or for reduction, and you have the two branches, and after you just measure the intensity and potential of the taffel to get the efficiency of your corrosion. But it's in presence of chlorine, salty water, so it's already activated.
Other questions? May I have one? In your opinion, which is the best composition for working in supercapacitors? Cobalt, nickel, aluminum, ternary?
Cobalt is more capacitive. There's a broader response because you have a much larger percentage of cobalt involved than nickel. Nickel is only a few percent, and you have to get a lot of default in nickel aluminum, and it's more Faradic. So it's a slower response. Combination of both would be of interest. Nickel is very pricey. Nickel is very expensive, so I'm not sure that we can, for a large diffusion of such electrochemical storage, I don't know if it's a good choice. Iron is difficult because iron is a low potential, like copper, but for anode it would be of interest if you are thinking of asymmetric system, so a positive and a negative electrode, and completely dissymmetric system for the supercapacitor. Maybe LDH cannot play the role for both, but I will suggest probably more the negative aspect LDH can play.
So the price will be the key in the end, no?
Yeah.
And just maybe a tricky question. I used to read a lot of papers coming from Asia in general, in which they analyze the capacitance properties of LDHs, and in some cases I was even reading values of more than 3,000 farads per gram. So could you please shed some light on that?
I would be very surprised if it's mixed with graphene, with nanotube, but you have to divide by the mass of the total electrode, not only by the active mass that you are using, because sometimes they are putting some electronic additives for the conductivity, but they divide by what they want. But you have to divide by the whole electrode capacity. So the capacity dropped down. 3,000 is a lot. I think 1,000 is already quite big. 1,500, I think it's record for now. But of course, if you mix that with ruthenium, with iridium, little particles, you can.
They were pristine at the end.
Boost depends on the electron. Electrolyte.
It's good to know. So sometimes
3,000 is a lot. And it was 7?
To the point they saw in the plot, yeah. But not a long analysis, no more than 1,000 cycles, I think. Other questions? Maybe we'll ask the last one concerning the coatings. So you mentioned that you use white LDHs like magnesium aluminum or zinc aluminum, but in terms of pricing, these are also the best options, or?
Yes,
okay.
Yes. The total site, or even zinc. We use zinc mostly because it's more crystallized, so we can follow step by step what type of chemistry we are doing, because we can follow that by X-ray diffraction, so we can see the stacking and also the loss of stacking, and we can, in fact, zinc and magnesium are completely reversible. We have a complete solid-state solution between magnesium and zinc in magnesium zinc aluminum. So you can change, but magnesium aluminum is very poorly ordered, and so that's the reason mostly we use zinc, and we can address mapping, for instance, and we can see more clearly. But magnesium aluminum is clearly of better price, and you have Sasol, you have Kizuma, you have other Korean chemical group. You have many groups now producing at a large scale tons of LDH, and mostly it's magnesium aluminum carbonate, to magnesium, aluminium, stearic acid for greenhouse, for many large applications.
And these coatings are used in commercial planes and cars. They are already on the market, or
No, transferring right now.
Okay.
There is a large number of patents because it depends on the politics of countries. It's taking quite a long time to transfer and to make it acceptable by a country in terms of changing its laws, changing its law, of course, and after to adapt all the company, because you have to implement this solution to what is already present in the company. To make short, it will be quite different to apply polymer coating with a filler inside or without a filler, because the volatile organic content will be not the same, the viscosity, you have a lot.
But yeah, probably the LDHs for coatings will arrive to the market before
I hope so.
the LDH for energy storage. No?
I don't know.
That's something very interesting for see the trends.
I hope together.
Yeah. Okay, so there are more questions. Otherwise, please join me thanking again the speaker.